This is actually what we were doing yesterday, but now I just wanted to show that it actually works because we had lots of problem with it yesterday. So this is just building the Barney's Valstar system, then equilibrating it and running it on an adaptive sampling method. So just go to cell run all because it takes like 4 minutes roughly to do everything. So if you go to cell run all, it's going to execute all of the cells. And then we can just quickly look through them while it's executing. So as we were saying before, if you've done this, if you started executing it, so we load essentially the two molecules, the one for Barney's, for Valstar. After we filter them to keep just the chain A because there were multiple chains, we set the segment IDs, the seg IDs for Barney's and Valstar to be separate for our building method, for the charm build. Then we also set different segments for the water. We mutated this residue here because otherwise we could not simulate it because we don't have the parameterization for this residue. And then we appended both structures together into one molecule so that we have them both together. We solvated the whole system. With we calculated like what the maximum distance was from the 0, 0 position so that we know how big the solvation box is supposed to be. Then we added a bit more so that we have some water around the proteins, but they are not exactly at the edge. We solvate it, then we build it using charm here, which is now being saved into the build folder inside this BB folder. Then we run a small equilibration. This time we corrected the number of steps here, so it's just 1,000 steps. It's a very short equilibration, but it's just to show you that it works. So this should take around. It actually finished already. Yeah, it finished. Okay, so it takes around 2-3 minutes to execute this equilibration, and then you create a production run. So you take the equilibration, the outputs of the equilibration, and they are being copied into a new folder, which will be used by the adaptive, which contains all of the options for ASMD to run the simulation, which are also being printed here. We define some extra options about the output files.
Just the license check. We didn't activate. Or at least that's what my log file says.
Because yesterday night I ran it and it was working fine, so like the exact script.
Open the terminal, see if you can run ASMD.
If I can run ASMD. Sorry? Yeah. Yeah, so it does have to do with the license check. I guess it expired from yesterday, no? Okay. Okay, so where was it? Do you remember, Johnny? It was. Sorry, yeah, in the main folder. Okay.
So everybody needs to do that.
Okay, so successfully checked out the license, and now.
Sorry, how do you check out this license?
You should have the file somewhere. This file called activate ASMD, probably in the main folder. Yeah. Yeah, just execute it, and it will activate the license again. So I assume if we run it from here again, no. Okay, from here on. Ah, okay, okay. So it didn't produce the output of the equilibration. Ah, that's why it finished so quick. Okay. So yeah, we need to run it again from this command here where we run the equilibration because the equilibration failed because of the missing license. So okay, this will take like 3 minutes. So if you want, just execute all of the rest here and where were we? So okay, so we prepare the production folder, so with all of the options ready for ASMD, and we save it into this folder called generators S1. So inside this folder generators, this simulation 1 will be used by the adaptive to start all of your new simulations. And here we define the options for the adaptive, which I'm going to talk about after the break. And yeah, and then we just run the adaptive, and if everything went fine, it's going to print here that it's running the simulation on your local GPU, on the one on the EC2 machine. Okay, so I don't know if we should wait now. I think it's gonna take a while, but you can go back to it and see that it has finished. So I'm going to just jump to the next session so that we do kind of the pre-adaptive stuff quickly, and then we'll do the break, and then I'll do the adaptive tutorial and how to write your own adaptive. So docking generators.
We leave that to the background.
Yeah, leave it running. Yeah, it's fine. Yeah, if you want, check after a while back, and it should say at the last cell essentially that it's executing the adaptive protocol. So here in this presentation, I just wanted to show you that if you want, you can also start essentially from docked poses. So you can use Vina, which we use internally in this dock command here. So you can use Vina to find some initial poses for your ligand, and then you can build systems out of them. And using again this equilibration and the production, you can prepare your system and simulate it or run adaptive on top of that. So actually, this is not the equilibration is not going to run now on your machines because it was I just tested it on a remote machine, but you'll see. So we can run the first parts though. So if we execute the first cells, the docking should finish quite quickly. It takes like I think 30 seconds maybe. So this again trypsin benzamidine. So as you can see here, we load trypsin, we center it, we load benzamidine, and then we do the docking. So we just pass two molecules, the protein and the ligand, and you get back the poses where you docked it and the scores that correspond to those poses.
So is this your own docking engine?
No, it's Vina. Autodock Vina, it's called, no? Yeah.
Yeah. We just simplify all the passing and stuff.
Yeah, I mean it has more arguments if you want in the dock method, but the simplest way of running it is just like this. So you give the protein the ligand. If you want, you can define also kind of a box where you want to dock, like an area where you want to dock.
If you know better docking program that you can use,
yeah, that's also
Go. We asked,
So okay, if you run the next command, so the only thing that I'm doing here is I'm making a molecule where I'm putting the protein, and I'm just appending all of the poses to this molecule so that we see where the poses are for the docking. And I'm putting here some visualizations, some nice views so that you can see the ligands better. So as you can see here, okay, it's made a bit of a mess because there are lots of poses on the same position. So just the visualization looks a bit bad, but it's all fine in reality. So there is one pose here by the docking. So essentially for all of these poses that the docking method found, we could look at their scores and like pick the ones with the highest scores and then start and build our new simulations from them, build our new systems. So here we can build a system. So I just made a for loop which iterates over the poses. Here I'm using actually this enumerate in Python. If you haven't seen it, it's just kind of a way of doing a for loop which also gives you an index and So if you pass it here a list, it will give you like the first list item plus the index. So it will start from 0, the I will go like 0, 1, 2, 3, 4, and the P will be the element of poses in position 1, 2, 3, 4, 0, 1, 2, 3, 4. So what I'm doing here, I'm loading again trypsin, the protein. I'm doing my typical stuff, so assigning segments to the protein, to the water, and to the calcium ion. Then I'm calculating again the distance of the protein. If you remember when I was building the systems for ligand binding, we want to position the ligand a bit further away from the protein so that's not interacting. So we load again so the ligand in this case, it's already stored inside poses. It's called P up there, so I just call it now ligand here. I assign a new seg ID to it and I rename it small just out of convenience. I put both into the same molecule. And then I solve it again in a box here, providing the Zamidin parameterization method and building for charm. I added this if here just so it doesn't take long, because if you like multiple poses and building is going to take, I don't know, 5 minutes maybe. I wanted it a bit faster. So here you can look again at the output where it tells you that it added some disulfide bonds. And it should finish, mine has finished already, building the two systems. Oh. More build, they misspelled it. No. Oh, this is not. Maybe I think I didn't execute it. Actually, I had executed it before, so this variable was not defined yet. But it should work for you now. I think the next command without an error. So the building just takes a bit. Yeah. Okay.
No module left.
Sorry.
The error. No module left.
Module left. No module. Did you import the module? Yeah, don't execute the equilibration. The equilibration, I know it will not execute from there on. From there on down, it doesn't work. I know. So I just, when I did equilibration, I did it in the lab, so I used our own Boeing equilibration. But okay, up to this point here where you visualize the build systems, it should work. Like here you're right. So once I do the equilibration folders, here I'm importing my own stuff. So if you replace this here with SMD local instead of SMD Boeing, so if you write here SMD local and you remove all of the arguments, I think.
SMD local, one word.
Yeah, SMD local, yes, with a capital L.
No.
So remove like all of this stuff here and just remove this stuff here, the imports, write here SMD local and remove the arguments.
Just write it.
Yeah.
So it's from SMD point to a...
But I will tell you not to run it because the equilibration is set to run for 1 million steps, so it's going to take again like very long. If you want it, use it to 1,000 steps. I mean, I just wanted to show you how you can essentially build a system from doc poses. I was not planning to execute it all through and simulate it. But yeah, in essence, essentially, if you replace this here with SMD local, and you remove these arguments, you uncomment the submit. It should submit all of the equilibration runs, and then it's going to retrieve. But if you really want to do that, reduce like this to 1,000 steps so that it finishes today. And then you can also do the production, which is going to generate your generators. So let's check back on the other one. It finished for you, not for me. Okay, this is my fault because I had run it already, but in your case I think it should have worked, no? The adaptive. I just ran it yesterday, so the files existed already, so now it complains that it has been run already. But don't worry about this. Okay, good. So I think we're gonna make a break now. and then we will start again to do the adaptive part. No, it's okay. Yes. Sorry. Okay, I'll take a look at it. But okay, work through. So okay, we'll look at it.
What was this? Can you go back to the other one where you changed this into the local thing?
Yes.
Yeah.
So in the submit commands from SMD local and any device you want to submit, you just pass it a list of folders which you want to submit. So in our model, essentially a simulation, all of the files of a simulation are located inside one folder, and you submit this folder to your device, like the GPU, and get simulated. Okay.
And that's submitted it. That's submitted it.
Okay. Yeah. Good. Okay, so yeah, let's take the break then. We'll do the break that was intended to be done later. I don't know what time is it? 5. What time is it supposed to be? Okay, yeah, we can make 20 minutes break and then we come back and we look at the adaptive samples. Okay, so I'll stop the streaming.